Welcome to our in-depth exploration of numbers in JavaScript. In most programming languages, you might be accustomed to having distinct data types for integers, short numbers, long numbers, and floating point decimals. However, JavaScript takes a radically different and simpler approach that you must understand to avoid calculation errors. In this environment, every single number you write, whether it is a whole number like 42 or a decimal like 3.14, is stored in the exact same format. We will dive deep into the IEEE 754 standard that governs this behavior, explore the limits of safe integer precision, and learn how to handle massive values using BigInt. We will also cover the built-in math library for complex operations and the peculiar special values like infinity and nan that arise when calculations go wrong. Mastering these concepts is essential for any developer who needs to perform reliable arithmetic or handle financial data without bugs. The most critical fact to internalize is that JavaScript numbers are always 64-bit floating point values. This means there is no true integer type under the hood. Everything is a float. This format allocates 1 bit for the sign, 11 bits for the exponent, and 52 bits for the fraction or mantissa. Because of this finite space, there is a limit to how large an integer can be before it loses precision. We call this the maximum safe integer, which is approximately 9 quadrillion. If you try to add 1 to a number larger than this limit, the result might not change, leading to silent and dangerous logic errors. On the extreme end, the absolute largest number you can represent is roughly 1. 8 times 10 to the power of 308, exceeding this massive value results in a special value called infinity. Understanding these boundaries is the first step in writing robust numerical code that doesn't break when data scales up. When you write numbers in your code, you are not limited to the standard base 10 decimal system we use in daily life. JavaScript provides convenient syntax for other numbering systems often used in computer science. You can write hexadecimal numbers, which are base 16, by prefixing them with a 0 and an X. This is incredibly useful for colors or bitwise operations. For binary, which is base 2, you use the prefix 0 and B, allowing you to write sequences of 1s and 0s directly. Octal, or base 8, uses a 0 and an O. It is important to recognize these formats because you will encounter them in configuration files, low-level data processing, or when working with hardware interfaces. Regardless of how you write them, whether as binary 101 or decimal 5, the engine treats them as the exact same numerical value during execution, converting them all to that standard floating point format we discussed. For representing real numbers with fractional parts, you have the traditional syntax, using a dot, like 3.14. However, for very large or very small numbers, scientific notation becomes your best friend. By appending the letter E followed by an exponent, you instruct the engine to multiply the number by 10 raised to that power. For example, 6.02 times 10 to the 23 represents the massive Avogadro's number concisely. A recent and highly readable addition to the language is the numeric separator. You can now place underscores between digits to act as visual commas. Instead of squinting to count zeros in a billion, you can write 1 underscore 000 underscore 000. The engine completely ignores these underscores during parsing, seeing only the raw digits. But for you and your team, it makes reading constants significantly less prone to error. This feature works across all number bases, including hex and binary. JavaScript provides the standard set of arithmetic operators you would expect: addition, subtraction, multiplication, division, and the modulus operator for remainders. A newer addition is the double asterisk for exponentiation. But for anything beyond basic school math, you will rely on the global math object. This is a library of static properties and methods providing advanced functionality. Need to round a decimal? You have distinct methods to round to the nearest integer, strictly down to the floor, or strictly up to the ceiling. Need to generate a random number? Math.random gives you a value between 0 and 1. It also includes utilities to find absolute values, calculate square roots, or determine the minimum and maximum within a set of numbers. You do not create an instance of math. You simply call these methods directly whenever you need to perform calculations more complex than simple addition. One of the quirks of JavaScript arithmetic is that it rarely crashes your program with an error. Instead, it returns special values. If you divide a positive number by 0, the script doesn't stop. It yields infinity. If you divide a negative number by 0, you get negative infinity. Perhaps the most notorious value is NaN, which stands for not a number. This appears when you attempt mathematically impossible operations, like dividing 0 by 0 or trying to multiply a string of text by 5. A critical trap to avoid is comparing nan to itself. Nan is never equal to nan. You must use the specific helper function number.inan to check for this state. There is also the concept of negative 0, which behaves like 0 in addition but can produce negative infinity when used as a divisor. Knowing how to detect and handle these states prevents your application from displaying nan to users. Slide 7. Because computers store numbers in binary while we write them in decimal, certain fractions cannot be represented exactly. This leads to the infamous floating point rounding error, where adding 0.1 and 0.2 does not equal exactly 0.3, but rather 0.3000000000004. This tiny discrepancy is usually negligible for general math, but it is catastrophic for equality checks. If your code checks if the result strictly equals 0, it will return false and break your logic. To solve this, you should never compare floats directly for equality. Instead, check if the difference between them is smaller than a tiny acceptable margin of error, often called epsilon. Alternatively, for financial calculations involving currency, it is best practice to convert everything to integers before doing the math to avoid these fractional artifacts entirely. For a long time, JavaScript was limited by that safe integer threshold we mentioned earlier. If you needed to track 64-bit IDs from a database or perform high-precision cryptography, you were out of luck. Enter BigInt, a primitive type specifically designed for arbitrary precision integers. You create a BigInt by appending the letter n to the end of an integer literal. This value can grow as large as your computer's memory allows, preserving every single digit perfectly. The catch is that you cannot mix BigInts with regular numbers in math operations. You must explicitly convert one type to the other. Also, since BigInts are strictly integers, division operations will discard any fractional remainder, rounding down towards 0. This is the tool of choice when precision is paramount and the values exceed the capabilities of the standard number type. While not strictly a number type, handling time in JavaScript is fundamentally numeric, because the date object is based on a timestamp, the count of milliseconds that have passed since January 1, 1970 UTC. When you create a new date, you are capturing a snapshot of that moment. You can extract the human-readable string for your backend using standard ISO formats, or use the modern internationalization API to format that date for users in their local language and style. It is important to remember that while the date object provides methods to get the day, month, or year, the underlying value is just a large integer. This allows you to perform date math, like calculating the difference between two events, by simply subtracting one date object from another, which results in the difference in milliseconds. We have now navigated the landscape of JavaScript arithmetic. You learned that the standard number type is a 64-bit float, capable of handling both integers and decimals, but subject to precision limits. We explored the various ways to write literals, from standard decimals to hex and binary, and the use of the math object for functional operations. We identified the dangers of special values like nan and infinity, and the inherent rounding errors that come with binary floating point math. We also introduced BigInt for those cases where you need to exceed the safe integer limit, and touched on how dates rely on numeric timestamps. With this knowledge, you can now write code that calculates accurately, handles edge cases gracefully, and chooses the right numeric tool for the job, ensuring your data remains valid throughout your application's lifecycle.